My name is Liano Perez, and I am a research scientist at Texas High Energy Materials and a U.S. citizen. I hold a bachelor and master's degree in physics, and am currently in a materials science PhD program at Texas State University. My father, Al Perez, is president and principal investigator at Texas High Energy Materials in Austin, Texas. He holds a bachelor and master of science degree in chemistry, is a U.S. citizen, and has been involved with the development and successful commercialization of polymeric materials for over 34 years. He has worked as a scientist at some of the largest and most respected companies in the world, as well as other successful small and medium companies in the United States. His professional product development and commercialization portfolio includes high-volume automotive products, functional coatings for heavy and extreme-duty applications, bomb blast mitigating armor, bonded solid film lubricants, coatings, adhesives, sealants, and novel composite systems. My father started Texas High Energy Materials during the darkest days of the severe 2009 global economic recession. The company has now been in successful operation for the past 12 years and counting. During the course of his first funded SBIR project through the U.S. Navy, he was the first to successfully microencapsulate highly reactive cyanoacrylate, crazy glue, for self-healing composite applications. In addition, his Navy SBIR project work led to a U.S. patent and also served as the basis of his Master of Science in Chemistry thesis work. In that undertaking, he developed an environmentally benign, non-toxic, corrosion-inhibiting extreme pressure dry film lubricant coating. That work would be further developed and tailored in a separate Air Force SBIR project for a very unique aspect of the variable speed drogue. As we speak, he is conducting pioneering work in the development of an entirely new, self-sealing, ballistically tolerant, crash-worthy fuel bladder for DoD combat aircraft. Together, he and I were one of the first companies ever selected by the Air Force for their new AFWERX SBIR program. Our Phase 1 project was compressed to 3 months, and the Phase 2 was compressed to 12 months. For that project, we developed a corrosion-inhibiting plasma electrolytic oxidation coating for light alloy secondary power system housings of fixed-wing combat aircraft. The V-22 tilt rotor Osprey provides the U.S. Navy with vertical takeoff and landing capabilities and the ability to hover. It is uniquely coupled with the speed and range of propeller-driven fixed-wing aircraft. The unique ability of the V-22's motors to tilt 90 degrees between horizontal and vertical orientations enables the aircraft to offer the best of both worlds of fixed-wing and rotorcraft platforms. Unfortunately, low-level hovering kicks up large amounts of sand, dust, dirt, mud, insects, and other foreign object debris, which gets ingested into the vertically oriented engine compartment. In addition, engine oils, fuels, and hydraulic fluids are, after escaping through old or compromised seals, inadvertently dispersed throughout the engine compartment and onto components. The combination of oils, solid debris, and mud build up on and foul the small aluminum tubes and fins of the heat exchanger surface. Fouling of the heat exchanger rapidly diminishes the cooling capability of the unit, which has led to grounded aircraft and unexpected mission terminations. The heat exchanger of the V-22 is not unlike traditional radiators found on passenger vehicles and semi-trucks. It is composed of fluid tanks with hot fluids that are circulated through the heat exchanger to reduce fluid temperature. Aluminum fins commonly found on radiators are also immediately recognizable on the V-22 heat exchanger. The lower right image of this slide depicts the actual hard-packed, almost cementitious fouling material that has caked over the cooling tubes and fins, rendering them ineffective. In this scenario, the aircraft fluids continue to heat beyond levels safe for flight. To prevent the costly fouling on the heat exchanger surface, we have been contracted to develop a durable, omniphobic coating that will immediately shed all water and oil-based fluids and pastes encountered by the heat exchanger, as well as bioorganic materials such as insects and bird strike debris. Note that omniphobic simply means an aversion to everything, in our case, resistance to both water-based and oil-based fluids, as well as solid organic and inorganic materials. The concept of self-cleaning omniphobic coatings is not new, and has been observed in nature for hundreds of years. The natural film on the surface of a lotus leaf is an excellent example of a self-cleaning coating. The principle behind natural and synthetic hydrophobic, lipophobic, and omniphobic coatings is focused on surface tension. We are all familiar with water beating up on a freshly waxed automobile. The applied wax coating has a lower surface tension than water, which causes the water to bead up rather than wet out and form a continuous water layer. The beads of water quickly and easily roll off the surface of the wax car panel. Dirt contained in water, also known as mud, also beads up on the wax surface and is easily shed. Rain-X is another good example of a hydrophobic coating that causes water to bead up and shed off a windshield surface. Omniphobic coatings have the unique ability to cause both water and oil to bead up on the coated surface and to easily shed off. As material scientists, we use a goniometer, an instrument with a funny name, to measure the contact angle of a fluid on a surface. We correlate surface tension from the measured contact angle. The instrument measures the contact angle of a fluid on the surface, either water or oil, which provides an indication of how well the coating under the drop can cause the fluid to bead up. Omniphobic self-cleaning coatings are a rapidly emerging technology and have many applications still waiting for their widespread availability. Unfortunately, there remains one major shortcoming of omniphobic coatings. They are fragile and have very little to no abrasion resistance. The premier abrasion-resistant coating chemistry used for aerospace applications is polyurethane. Our goal is to develop an omniphobic self-cleaning coating with the durability of polyurethane, to prevent fouling of V-22 heat exchangers after repeated abrasion by sand and debris being ingested by the hovering aircraft. As an added challenge, our coating must be very thin. The polymers we use for coatings are predominantly insulators of both heat and electricity. A thick coating on a heat exchanger will diminish the ability of the unit to reject heat of circulating fluids flowing through the exchanger. Because the tubes and fins of the heat exchanger are small, with some positioned deep within the unit, traditional coating application techniques like brush or spray are unable to provide complete coverage. Therefore, we have turned our application approach to chemical vapor deposition, also known by its acronym CVD. In this application method, the part to be coated is inserted into a closed chamber and under vacuum. The chemicals reactants that will form the coating are vaporized, allowing them to permeate and deposit onto all exposed areas of the part. Think of it as a way of immersing the part to be coated into a chemical bath that is a vapor fluid rather than a liquid fluid. The progress of our research and development project finds us at a TRL level 4, and at the end of our project is expected to reach TRL 6. The project Phase 2 base has an end date of August 2022, and the Phase 2 option has a February 2023 end date. We remain hopeful that the global supply chain disruption caused by the COVID pandemic will not adversely affect our project. To date, we remain on time and under budget. To date, we have completed our first 3 project milestones and are nearing completion of the 4th. The first milestone was to determine the coating chemistry that could best meet all performance aspects of the project. The second milestone was to apply the coating on 6061 T6 aluminum test coupons, which are representative of the same material used in the construction of the heat exchanger tubes and fins. The third milestone was to evaluate the performance of our coating technology on representative coupons. We continue to focus our efforts on completing milestones 4 and 5 on time and under budget. Milestone 4 is application of our coating technology onto a small-scale heat exchanger. Milestone 5 is completion of our durable self-cleaning coating technology on a small-scale heat exchanger. The 6th and final milestone will be application of our coating onto a full-size heat exchanger. The key feature of our novel coating is its omniphobic self-cleaning capability combined with the durability of wear-resistant polyurethane coatings. As we previously stated, currently available omniphobic coatings provide excellent anti-fouling performance, but are unable to endure even mild abrasion wear. Our coating technology ties the unmatched abrasion resistance and durability of the best polyurethanes used in aerospace applications to the self-cleaning performance offered by existing omniphobic coatings. Our product also offers very low thickness profiles of approximately 10 nanometers, which prevents it from negatively affecting the performance of the heat exchanger to cool fluids flowing through the unit. Our transition plan to PMA 275 V-22 Osprey includes successful flight qualification tests by the end of the project. Our project technical point of contact, Mr. Kurt Prescher, is our primary transition advocate. Our novel self-cleaning coating technology will also have immediate performance benefits to other aircraft also afflicted by fouled aluminum heat exchangers, or other aluminum engine components that operate near the same temperature ranges of the V22 heat exchanger. This includes the H-1, UH-60, CH-47, and CH-53 helicopters, as well as the emerging Defiant X and Raider X vertical lift aircraft. All of these aircraft kick up sand, dirt, and debris at low altitude hover, which produces a sandblast type of wear on critical heat exchangers and other drivetrain components. A durable, omniphobic, self-cleaning coating will also be highly beneficial and cost-effective for heat exchangers found in non-DoD applications, including oil and gas, power generation, refineries, and municipal facilities that utilize aluminum construction heat exchangers. In transitioning our coating technology to the Navy fleet, our technical team will design and deliver the hardware equipment necessary for proper coating application, including user-friendly software that can be used at the maintenance depot level. Training in the proper use of the application equipment and safe handling and storage of the chemicals used to produce the coating will be provided. Direct interaction with manufacturers of heat exchangers will provide the opportunity to institute industry-recognized quality programs and serve to expedite the transition of the coating to the fleet. Production can be ramped up in under 20 months. Coating application equipment can easily be designed to accommodate even the largest engine components. Keep it flying, keep it clean. Thank you for your interest and attention. We are available to answer any questions or suggestions you may have regarding our novel self-cleaning coating for the V22 heat exchanger. Come and talk to us about your materials development needs for even the most demanding DoD applications. Our ideas have successfully come to life through the SBIR program. From idea to feasibility to working prototype and ultimately to transition and production. We've been there. We can help.